If you're short, I'll just borrow hers right now.
I have the printout.
Okay, this is inclusive. Good afternoon, everybody. We're glad to see all of you. Some of the people I talked a lot on the phone. Nice to see the faces. I'll try to make it not too complicated, and actually it's not complicated. By no means this little write-up is something that we should be proud of in terms of the presentation or whatever, but at least I hope it's practical, and nobody here will become a PhD in fiber optic inverters. That's not even the intent. What it tries to do is to give some of the basics, prevent situations that we do over-design. With a little more effort, I think anybody here can, with a big portion of the customer in a position that the customer will think that they know a lot. There are customers out there that will teach us things. And as we go ahead, we actually will continue to improve our training material. So it's not that we know all kind of people, but I think we can go up to the next level in terms of the knowledge, prevent mistakes in design, being able to almost intimidate 80% of the customers. From the other 20%, probably we are going to learn, because they're very sophisticated people from time to time out there. It's not like that we know everything. Another comment that I wanted to make, yes, there will be some emphasis on fiber, some on the wall street aspect of it also, to move our positioning from being a low-end 10100 switch provider. But I want everybody to remember, a building has many components to it. It's only one another component. I think it's a pretty strong component, but it's only one component. I heard a little bit of Tim's presentations, just a nice example how several aspects of our technology as a combination are winning, But don't misunderstand, Mark, that now we are pushing you back to sell only transceivers. I look at it as a potential door opener in specific situations, a little edge in some situations. We have to increase our knowledge in many, many other aspects of the product, not only this. And I think that's one of the things that Manix and Yechiel will take upon themselves. Internal training. Don't promise you many more situations in such hotels, but we'll find some cost-effective ways to convey the knowledge from R&D to everybody in the organization. Okay. When I finish, maybe I will tell you a little bit about general outlook of the company, what are the thoughts up there in the corporate headquarters, wherever it is. I don't know where the headquarters is. Okay, I will try to follow the write-up a little bit, because I think that will be the simplest. Of course, the product specification I will not go over. It's something simply to be read. And this is the basis for every design. Yes, Tim, you already have a question?
There was a question on the saturation on this chart.
Yes.
What does that represent?
Yeah, that's a very good question. We'll get there in the text.
Okay.
But when I go to the next page. One thing to note that we eliminated the SY category, and I think when we'll go over some of the calculations, you will understand why we did it. If you still remember what our unaudited literature was saying about the SY. It's something that simply will not work. Will not work, period. I don't know. Okay, so we have, first thing I will brush through very quickly on the different licenses that are used in most of the applications. And I will not cover all of them. Because we have the first category is LEDs. And actually, here, there are two ways to divide it, even though MRV does even a third category of LEDs. We have the surface emitter and edge emitters, it's one category. And you have by wavelength. So you have 850 nanometer, which, by the way, where all the fiber optics started from these light sources. Surface emitting 850 LEDs, And you have, of course, 1300. And MRV is still selling even a 1550 LED, but this is a curiosity. It's nothing more than that. So, in terms of the spectral properties, it's a very wide spectrum source. The surface emitter is 1300 nanometer, for example, and 120 nanometer wide. And 850 is something quite similar. I didn't even describe it too well in the write-up. Let's be practical. What we are using for the surface emitters, they are very stable in temperature, by the way, the surface emitters. And they are used strictly for multimode. They're all 10 megabit, some token ring, 4 megabit and 16 megabit products that you are selling still from Maryland. And typically, power emission is into fiber, rather, coupled fibers around minus 14 dBm. And they're used for 2 kilometers, usually multimode fiber. And data rates, I would say, up to 25 megabits. I don't know of any usage that is really widespread with it's above. It's not necessarily a physical limitation. You can go to higher, probably, but I don't know of any protocol. The truth of the matter that the FDDI, 9-pin FDDIs that we're finding in many other products, it's 100 megabit, is using this LED. You know what I'm talking about, right? So all the uplinks of the Megaswitch 2 and the 2001, based actually also on this. So somebody can actually nail me down that what I wrote there is not absolutely true. There's one LED that for multimode. The next type of LED is that we have very little usage of is edge emitter. Edge emitter. And we do it only for data communication only at 1300. You guys are not really using it at almost in any product. The only product that I can think of is the MX type. You know, we have a 301 MX, NX300 MX. It's a multi-mode for extended distance. You know, it's using 1300 nanometer. It actually can couple huge amount of power into multi-mode. Pretty distant to single mode, but we don't use it for single mode applications. As MRV, we have a lot of customers that will buy it to make some proprietary data links for single mode. But we, as an NBase company, the only place where we have this is actually in the MX type products. I think it's appearing here. Yeah, 301 MX. And it's really a product that has terrible temperature variations. Edge emitting LEDs are varying in temperature a lot, but usually it's sold to environment like computer room environment, not really stringent atmospheric conditions, so it's selling quite nice actually. So that's for LEDs. We have the Fabry-Perot lasers, FP lasers. And again, I don't want to make a big confusion. You know, we sell also 1550 FPs. Bart probably remembers one customer that we did some special product. I try to focus on what we really do on daily basis. So we really only talk about 1310. Okay. By the way, I'm confusing between 1300 to 1310. It's really 1310, the zero dispersion point for the non-dispersion shifted fiber, meaning the fiber that is installed in most places except Japan. So this is the wavelength. And Fabry-Perot means that the power spectrum looks something like this. There's several modes. And this is lambda C, the center. Again, what I wrote is not complete, but there are different things that we have to add later. For example, this will change in all the NBase products with temperature because we don't use cooler, thermoelectric cooler, even in one product of NBase. We sell quite a bit of cool devices to the outside world. But this is the reality of datacom. We don't use cooler. So actually, this will shift with temperature, just for your own reference, at a rate of 0.4 nanometer per degree C. This is important because what it does is that the calculations of attenuation, you have to take it into account. Not everything remains optimum. Again, most situations you are in a computer, the wiring closet, whatever. So it's around 40 degrees C and you forget about it. But it's something to remember. Another thing is the so-called delta lambda, meaning the full half-width max is around 3 nanometers. And again, I will not start to do calculations, or I think in the glossary there is some indication to that, but not necessarily. If somebody is interested, we can provide him more information. This is what will determine the dispersion limitation of this type of light source. And there is a limitation. The write-up elaborates on it, but it's a rule of thumb, and it's pretty conservative, but I prefer to be conservative, even though I'm orthodox. It's 1.2 gigabit, 1.25, this is the really data rate of gigabit, 6 kilometers. OC12, 12 kilometers. It's conservative, really. Somebody can argue that it's actually 10 kilometers. But then I ask them, what temperature range, what exactly is the fiber quality? 6 kilometers, we are very safe. As we all notice, the LX module, in terms of the standards, they put it on 3,000 meters. So if you want to follow the standard, the 6,000 meters that we are talking about is already non-standard. But reality, we all know that from our own experience, many others, that 6 kilometers is a conservative number for single mode fiber for gigabit. But this is a light source that we are using. Okay, where we are using it? In all our modules, single mode modules, up to the SX level, SX grade, including SX. Okay? In gigabit, this is what we use for the low grade, which I think is called S1, right?
Yeah. S1.
Incidentally, we use it also for multi-mode applications in gigabit. It's the only place that we use Fabry-Perot lasers. We don't have a good LED that will go up to gigabit. Nobody has. So we use this also for multi-mode. The other type of Fabry-Perot laser that we are using, it's almost Fabry-Perot, but not really. It has usually only one mode. There's 850 nanometer lasers. It was or 780 even. This was really forced on us, force majeure, so to speak. There are people that have nothing to do but sit in committees, and the gigabit standard committee decided to make everybody's life more miserable. So we have 2 light sources approved for multi-mode applications. If you read, again, the little booklet, we elaborate on it. It's pretty crazy.
What I heard you say is there's 2 light sources for gigabit. One is the 850, which was set by the standard committee. One was 1300,
Which was also set by the same standard committee for multi-mode application. One is called SX, the other is LX. It's pretty crazy. I'll explain why it's crazy. Traditionally, the 10 megabit developed first, 4 megabit, 10 megabit, in a time that data rates were low, and the only light sources that were available initially were 850 nanometer LEDs. Then it moved to 850 lasers, CD-type lasers that are being used now. You can buy them $4 a piece. And we're talking 25 years ago, 20 years ago, it started to move. And then the long wavelength technology, the 1310, 1550 technology started to come in. And that was very good when I joined the fiber optics world. They were doing trunking, not so much LAN activity at all. So 565, it was first, I think, 135 megabit, then 565. When I left Caltech, was Fabry-Perot technology, cool devices, up to 30 kilometers. That was the technology. When it started to go with the OSIS standard, you know, the ATM, so we have, okay, FDDI, put it on 1300 nanometer. Fast Ethernet, same thing. OSIS 3, same thing. OSIS 12, same thing. OSIS 48, same thing. OSIS 192, long wavelength, everything long wavelength. Suddenly in the middle, between OSIS 12 and OSIS 48, they decided that life is too easy, and we have suddenly two light sources that don't talk with each other. And Matthias probably can tell us a few horror stories from the field. And, but this is the situation, we have to tackle it. So we have this type of lasers that trying to do the multi-mode job. And probably they do it for 300 meter, and even the fiber is very good, probably up to 500 meter. And we, by default, use this technology to do the LX type. So we found ourselves buying the modules, the SX modules, just like we buy the multi-mode modules for fast Ethernet. Cost is around $110, $120. Doesn't worth for us even to do it. One of the things, by the way, that propels this to existence, the fact that some of the big companies like HP and Honeywell had vested interest in a new technology called vertical cavity surface emitting lasers. And supposedly it's going to be much cheaper. It's really a joke because the cost is not the laser diode anymore anyway. And that's what happened. So we have to be aware of this. One of the things that this difficulty, of course, can create is some little business. So somebody bought this, and suddenly you have to change the cabling, and he has a problem that he needs single mode, so we have wavelength conversions already available. But actually, it's a pretty big nuisance. That's the reality. Now, to break the dispersion distance,
Can I interrupt you?
what?
Can I interrupt you for just 1 second?
Sure.
Can you please explain dispersion and what it is, how it's received, what the problems are?
So I will do it in a very, very simple way, so not to make out of it an academic presentation here. Maybe if I wanted to do it academic, I would send somebody else here, you know, maybe in the foundry some PhDs, and they will give you formulas until you stop them immediately. but basically what happens, from an empiric, practical point of view, the propagation of different modes of that, you remember the Fabry-Perot, inside the glass is different. So you have, if you have a signal that is the time domain, the delta function, infinitely narrow, so we are broadening because of the different speeds of the propagation of the different modes. You might ask, who cares? I'm not dealing with delta function. For a NRZ signal, when you have a signal, what it will do, it will make you fuzziness, you know, in the boundaries. It will broaden it. And thus, will limit at the end the data rate. Practically, what it means, people design the fibers that now in the ground. And it was a big hoopla when I left Caltech, that maybe they will do a new type of fiber. It's called dispersion shifted to 1550, but the way it developed after the long wavelength technology started to establish, they designed the fiber in such a genius way that this broadening is minimal at 1310. For that type of fiber that we have millions of kilometers in the ground. Now, one country in the world, namely Japan, put fiber that is the minimum dispersion. So if there's a function that will determine that broadening, it has a minimum 1310. So it will enable the highest data rate on that fiber to the longest distance. The Japanese made a fiber that will peak at 1550. It's called dispersion shifted. And there was a lot of talk that we'll do it also in the US. The reason why it didn't happen, because there was already too much fiber for the first time. Now, what's the reason to do the 1550? You can guess it from the table that I gave you here. On the page, there are pages here? No pages. So, man, it's one of the improvements that we can do is add pages. So 1, 2, 3, fiber lost at different wavelengths. If you look, 1550, I wrote a broad range just to cover a very, very practical situation. But you can go down to 0.2 or even slightly lower attenuation. And that was the reason why the Japanese really installed 1550. I mean, dispersion shifted fiber. But anyway, from empiric point of view, the dispersion is to the level of broadening of a signal. And what it means that at any certain data rate, you will be limited by distance or vice versa. Okay? The same distance at higher data rate, at a certain point, you'll close the eye on the eye pattern, no detection, no. Okay, so in terms of the light source that take care of the dispersion issue, at least to very, very long distances, very high data rate, is of course what we call distributed feedback lasers, which have one single frequency, and they can be made in both wavelengths, both 1310 and 1550. And the power spectrum looks like this. I mean, there's only one mode that is supported. And how it is done, it's quite interesting. We are now doing it at Chatsworth, actually. And of course, the driving force behind this, when I hired the guys to do it, probably 2 years too late, by the way, too much geared towards switches. The thought was cable TV, some very highly linear lasers for transmission of 18 channels of video. Found out that we actually more a data company than analog company, even though we have some very nice analog product that we are selling. And now what's geared, the main gear is WDM applications. So they are doing actually lasers like this with delta lambda less than 0.1 nanometer at different wavelengths. And as I said, we are making WDM for the poor, so we don't go ITU grid. We do it very far apart in the 1550 nanometer window. Strange wavelengths, 1500, 1520. But the good thing is that at the 1540, just by selection, we are finding ITU grade lasers. And as I said, we sell them to finance R&D. $2,000 a piece, which is a huge discount versus what you have to pay if you want to buy it from Fujitsu or other places. But basically this, by virtue of being only one mode and so narrow, in terms of the dispersion limit for 1 gigabit or 1 to 5 gigabit, it's more or less 180 kilometers on non-dispersion shifted fiber. And this is in the condition like NBase is doing it, meaning that the laser diode is directly modulated with electronics. But it turns out that when you directly modulate the light source like this, there is an effect called chirping that is not mentioned here. But it's actually some kind of broadening, a little broadening. And that's the reason why it's only 180. Otherwise, other technologies is to take the light and modulate it, I mean, bias the laser at constant current, no modulation, and modulate it, external modulation, modulate the light. You can think about a quick chopper, right? Try to have a chopper at gigabit. So they do it differently, of course. They do it with lithium niobate technology, which is very expensive and its own problem. But if you use that technology, then this limit falls apart. You can go 1,000 kilometers. Of course, then you have a problem with attenuation. Attenuation will kill it. But that's why we have EDFA, erbium doped fiber amplifiers. Currently in MRVs, the basic technologies to make fiber amplifiers exist. the first WDM that we are going to use, though, I mean the first box that we described in the write-up that we talked about, no amplification, everything straight out of the box, minimum cost. And that's why it's limited to 10 dB by virtue of power budget, not dispersion. When we move to OC12, 2.4 gigabit, so this distance start to drop. You know, it's actually, maybe I'm a little bit mistaken here, but I don't know. Now it looks a little bit better than I thought even. It looks around 90 kilometers. For some reason I thought that I have to go over the numbers, that the dispersion limit will be about 50 kilometers, so it will be exactly the same point where the budget link will stop. I'm not sure now, but anyway, this will be our next maybe 3 quarters from now, or 4 quarters from now product, and in this case, it will be definitely dispersion limited below 100 kilometers. Anyway, let's talk about a few other things. I described basically, let's just summarize quickly. I talked about LEDs, Fabry-Perot lasers with some of the limitations, and we talked about the device that we need to break dispersion problems, which is single frequency lasers. As a rule, 99% of the cases, whenever we have to break the dispersion, when we have to use DFB lasers, we have chosen to use 1550, not 1310. The reason being because until we do the chips ourselves, a process that starts to take place now, more or less, just like with the 3101, you know, give us another quarter until we pull in. Until that time, the laser cost us a lot. We had to buy it outside. It didn't make a big difference. Once you go single frequency, it's big added cost. So the common sense say, if you do it anyway, such a high price, let's do it with the laser that give you longer distance. And of course, this table 3 shows why. Because 1550, the attenuation is almost half than the attenuation of 1310. Okay, let's go to some practical budget calculations. I'll explain you why we are talking budget. If the data rate is low, meaning fast Ethernet or even OC3, using Fabry-Perot lasers, you never talk about dispersion because the data rate is low. So dispersion is not an issue. So the only way to determine if a link will work good or bad will be budget calculation, meaning power attenuation will be the main problem. When you go to 1550 DFB, the same thing applies even at higher data rate, that you again just have to worry about budget calculation. So, let's talk about the saturation issue on the mind. So there are three parameters when you do design a link, that you're assuming the dispersion is out of picture. And again, when it's out of picture, either when you use single frequency laser or you are at low data rate, like